To best of my knowledge, John's interests have mostly been focused on reflection groups, Coxeter groups, braid groups, and Artin groups. And so he has kindly accepted our invitation to give a talk on the interesting topic of the mysterious geometry of Artin groups. Okay, John, please. Yeah.
Okay, thank you. I'm very happy to have this invitation. I'm happy to speak to you today. I'm aiming this at a broad mathematical audience, so hopefully it's not, hopefully there's something there even for the people who are non-experts or far from the field, but also not too boring even for the people who are more experts. A very wise senior mathematician once told me that when you're giving a seminar talk, you're representing yourself, but when you're giving a colloquium talk, you're representing your field. And so my goal in this talk is to give you a sense of the field of Artin groups and what people are doing, what they are. I'm not assuming that people know what an Artin group is. In fact, here are the main goals in my talk. What I'm planning to do is I want to give a sense of Coxeter groups, where they come from and how they arise as generalized symmetric groups. Then talk about Artin groups as sort of a braided version of a Coxeter group. And then the main thing I want to do is highlight the major differences between the two of them. These are two general classes of groups that contain lots of different examples. They connect up to lots of different parts of mathematics. And as a short summary, there are just many, many results that we know about arbitrary Coxeter groups. And there are actually extremely few results that we know about all Artin groups. There are some. We know some Artin groups very well. We know some parts of all Artin groups very well, but there are very few general results. And it's in that sense that Artin groups are much more mysterious than Coxeter groups. And so let me start by just defining what they are. But then after the definition, then I'm going to start with a definition that's strictly in terms of presentations, generators, and relations. But then I'm going to switch to a more geometric approach to sort of talk about where they come from and why they're important. So hopefully people are familiar with generators and relations. Not all parts of mathematics use this, but the more algebraic side, of course, does. If you have two generators of a group, two elements of a group, A and B, you say that they satisfy a braid relation of length m if the words AB, AB, ABA and BAB, ABAB are equal, where you've used the same length. And so, for example, here is the braid relation of length 2. It's just the commutation relation. The braid relation of length 3, this shows up in the standard definition of the braid groups. Braid relation of length 4, these are sometimes called Artin relations. And then an Artin presentation has at most one of these relations for every pair of distinct generators. And I'll give an example on the next slide. A Coxeter presentation is very similar, but you also add the relations that say that every generator is an involution. Every generator squares to the identity. And then a Artin group is anything that's defined by an Artin presentation. A Coxeter group is defined by a Coxeter presentation. So let's go ahead and take a look at, you usually encode these in diagrams. And so there's some conventions, and I'll call these the classical Dinkin conventions and the modern presentation conventions. Basically, you want to write down a graph with as few labels as you can get away with. And so you take the things that are most common in your graph, and the types of relations that are most common, and you don't draw them. And so the Dinkin conventions that show up from Lie algebras, from when you're looking at the diagrams for Coxeter groups, all of the pairs have relations mostly. And so there's lots of commutation relations. And so we say that if there's a commutation relation, we don't draw an edge. If there's a braid relation of length 3, ABA equals BAB, then we don't put a label. And with these conventions, it makes some things very nice and apparent. Let me actually go ahead and skip the convention. Let me get to the example. Okay, just so that people can see what we're talking about. So if you take this little graph that I've got drawn in front of you, it's got 4 vertices, which I'm going to use as my 4 generators, A, B, C, D. And then for every pair of vertices, in this case, using the conventions, there's a relation. Since I don't have a label, this is implicitly a 3. This is a 3. This is a 3. This is a 3. If there's no label, it was a 3. From A and D, since there's no edge, that's implicitly a 2. And so A and D end up commuting, and then all of the others end up having these relations, ABA equals BAB, etc. And so this is a very simple group. It's got 4 generators. It's got 6 relations. We can see that it's an infinite group because if you just send all the generators to 1 inside the integers, you can see that this maps onto the integers. So it's clearly an infinite group. But you might ask yourself, what else do we know about this group? If I gave you a word in the generators, if I gave you a string of A, B, C, D, A inverse, B inverse, C inverse, D inverse, some complicated word, and I ask you whether it represented the identity in the group, could you tell me? This is something that you might expect to be a fairly straightforward idea since the relations are of such a simple form. They're not complicated. It looks very simple, but we know from looking at the history of group theory that things that look simple can often be quite complicated. We know that there are groups with finite presentations where it is not possible to write a computer program to answer the question whether or not a word is equal to the identity. And in fact, one of the points of this talk is that for this group, we actually do not know how to solve the word problem. This is a group where we have no idea which words are equal to the identity. We can prove that certain words are not equal to the identity, but in general, this is actually a very mysterious group, believe it or not. It looks very simple, but it's actually more complicated than you might imagine. Let me now go back and talk about where these groups come from, because like I said, when you look at presentations can easily lead to intractable problems. And so most of the times when you're looking at a presentation, you want to have some good reason why you're looking at that presentation. There should be some motivating factor. And with Coxeter groups, they do have good motivations. The spherical Coxeter groups really start life as looking at groups generated by reflections acting on nice spaces, acting on spheres, acting on Euclidean space. They came up for Coxeter himself when he was studying what are called regular polytopes, and they show up in Euclidean space as everything develops in terms of Lie theory. The usual aspect in Lie theory is you start with a Lie group. It's a manifold which has a group structure. You look at the tangent space of the identity, you get a Lie algebra, which is a vector space with a bracket. You look inside there and you find a maximal commuting subalgebra with the null bracket, which is a Cartan subalgebra. From that, you can end up finding a discrete group acting on a Euclidean space. And as you try to classify the discrete groups acting on Euclidean space, you end up finding what are Euclidean Coxeter groups or affine Coxeter groups. And so the spherical Coxeter groups and the Euclidean Coxeter groups both sort of naturally arise when you look at generalizations of the Platonic solids, or you look at the classification of semi-simple Lie algebras. These are the key examples. And when Jacques Tits, as part of Bourbaki in the early 60s, was writing down the Bourbaki books on Lie groups and Lie algebras, he had to write down the foundations of the affine and spherical, particularly the affine Coxeter groups. And as he was writing down the foundations for affine Coxeter groups, the affine groups generated by reflections in Euclidean space, he realized that all of the constructions were completely general. And from that, he ended up defining a general class of groups called Artin Groups, or Coxeter Groups. We'll get to Artin Groups soon. He also invented Artin Groups. The spherical and Euclidean Coxeter groups are usually listed in terms of their Dinkin diagrams and extended Dinkin diagrams. The Dinkin diagrams come in 2 flavors. There are 4 infinite families. If you exclude the white dot, then you get the diagram that's encoding all of the group that's acting on the sphere. And if you include the white dot, then you end up getting a diagram that encodes the action on the Euclidean space. And I'll talk about the encoding in just a second. It's part of the diagram conventions, but hopefully you've at least seen the type A, C, B, D Dinkin diagrams. These should look somewhat familiar. The tilde says that you've included the white dot. You exclude the tilde if you're not including the white dot. These show up in so many different parts of mathematics. I imagine that everybody has at least run across the diagrams, even if they don't work with them directly. The perspective that I want to take is that what these are really doing is that the Dinkin diagrams and the extended Dinkin diagrams are really encoding the shapes of simplices in spheres and in Euclidean space, where every dihedral angle is pi over k for some k, where k is an integer. So for example, in the Euclidean plane, we can write down a 30, 60, 90 triangle with angles pi over 6, pi over 3, pi over 2. And this corresponds to the diagram called G2 tilde. The thing that's nice about simplices with dihedral angles of this form is that if you reflect in the faces of the simplices, the maximal faces, the facets of the simplices, you end up getting a nice tiling of your space. And so, for example, let me go ahead and if you take a triangle, here's an example of a connection between a regular polytope. Cubes are regular polytopes. Cubes are one of the Platonic solids. They have a symmetry group that moves all the vertices around. It's highly symmetric. And if you look at the reflection symmetries of this group, you can end up chopping it up with various hyperplanes that will send the cube to itself when you reflect through, like the yellow hyperplane, so there's all these different hyperplanes, like this blue one, that would reflect side to side. It chops up the cube into 48 different tetrahedra. And the fact that this is a regular polytope basically says that it's acting transitively on these simplices. That when you look at the isometry group of the cube, you can move any of these simplices around to any other simplex. And it's a Coxeter group generated by the reflections in the sides of this green tetrahedron. So if you reflect with respect to this side, then you can get the yellow reflection. If you reflect with respect to this side, you get the red reflection. And if you reflect with respect to this side, you get the blue reflection. And I'm doing it for the cube, but you can imagine that if I took a small sphere around the origin, what I would see is a small sphere that was chopped up into 48 different spherical simplices. And this would end up giving me a tiling of a sphere with a little spherical triangle that has very nice dihedral angles. And so this is an example of a spherical Coxeter group and one of the origins of the spherical Coxeter groups. Here's an example of the G2 tilde, where if you start with a triangle that has pi over 2, pi over 3, pi over 6 sides, and you reflect, you can tile the plane. What Coxeter was really doing was he was trying to understand what was going on in higher dimensions, and are there other examples of nice angled simplices in higher dimensions on the sphere or in Euclidean space. And in particular, he ends up, are there higher dimensional analogs of the cube? Of course, there are n-dimensional cubes. There are n-dimensional simplices, but what else is there? And now just some pretty pictures. So here's an overview. All the finite Coxeter groups basically either come from regular polytopes, or they come from Lie theory, or both. And so everything that we see in the world of nice little finite groups of symmetries generated by reflections, they come from one of these two sources, either if they're from polytopes or they're from Lie theory. And let me say a little bit more about a regular polytope. I won't go into the full definition, but roughly speaking, a regular polytope is just any convex hull of a finite set of points in a Euclidean space that is as symmetric as possible. And what that means is that its isometry group is as symmetric as possible. It means that the isometry group should be able to move any vertex to any other vertex, any edge to any other edge, any two-dimensional face to any two-dimensional face, and so on. But also, if you give me a vertex inside an edge inside a face, and then a second vertex inside an edge inside a face, those are called flags. And for any flag, you should be able to move it to any other flag. And so this is what it means to be regular. It's a really, really restrictive condition. It turns out that if your polytope is regular, then its isometry group has to be generated by reflections. And in fact, the isometry group has to be one of the finite Coxeter groups. And Coxeter has a very nice theorem that ends up saying that every regular polytope, in low dimensions, they're the examples that you would probably guess. In one dimension, the only regular polytope is an interval. That's actually the only interesting polytope. In two dimensions, the regular polygons, the regular m-sided polygons are the regular polytopes. In three dimensions, this is the classic theorem that there are exactly 5 regular polytopes in 3 dimensions. These are the 5 Platonic solids. In dimension 4, it turns out that there are 6 regular polytopes. And then once you get past dimension 4, the only regular polytopes are the high dimensional simplex, the high dimensional cube, and what's called the dual of the cube, which is sort of a high dimensional generalization of an octahedron. It has various names, none of which are very good. It's sometimes called a cross polytope. It's sometimes called an orthoplex, but it's really just the dual of the cube. And so if you've never seen this theorem before, one thing that this should really, one thing that should intrigue you about it is what's going on with these 6 regular polytopes in dimension 4. Everything else is sort of not that unusual. That intervals, regular polygons, Platonic solids are all very familiar. High dimensional simplices, high dimensional cubes are things that we can sort of think about. But there are some strange things that are happening in dimension 4, and it would be really nice if we could see them and understand them. And so even if most of the rest of the talk doesn't make that much sense to some people, I want to at least advertise a nice technique for viewing things in 4 dimensions that is useful. And so to do this, what I want to do, I've got the next couple slides are all just pictures. What I want you to do is I want you to think about how would you explain a 3-dimensional cube to someone who couldn't visualize 3-dimensional space. And so normally what we would do is we would draw something like this to represent a 3-dimensional cube when we draw it on the blackboard. But if you can't visualize 3-dimensional space, then this is actually a very, it's not a very good description, because if you can't visualize 3-dimensional space, you can't really tell what the edges are and where all the crossings are. I mean, this is exactly what you would see if you actually held a 3 cube at arm's length. But like I said, if you can't visualize 3-dimensional space, then this is not very good, because it really is confusing when you stare around here. If I said, how many squares are there? Well, it looks confusing because they're all crossing. But there's another way you can do this, which is that you can look at the cube very, very close up. Instead of looking at it from arm's length, if you look at it very, very closely and you look through one of the square faces, then here, none of the edges are crossing anymore. And now you can see everything. And so basically what we're doing is we're taking one of the 2-dimensional faces and we're looking inside the room at the rest of the boundary. And as we see the rest of the boundary, we see a subdivision of this square. And we get this nice planar picture that lets us see all 8 vertices, all 12 edges. And we can actually see that there are exactly 1, 2, 3, 4, 5, plus the one we're looking through, 6 square faces. And this idea can be used one dimension higher, because what you can do is you can say, what if I was trying to describe a four-dimensional polytope, but I can't visualize four dimensions? Because I can't visualize four-dimensional polytopes, what I'm going to do is I'm going to have somebody who lives in four-dimensional space put their eye very close to one of the three-dimensional polytope faces of this four-dimensional polytope and look at the rest of the three-sphere boundary. And as they look through one of the three-dimensional faces, they will end up seeing a subdivision of that three-dimensional face into smaller pieces that should be the analog of what we did here. And so if you do that with the four-dimensional cube, you end up getting this subdivision of a three-dimensional cube into smaller things. And so here, hopefully, you can see that. Oops, nope. Nope. Hang on. That's the one I want. That here, going down to here, there is sort of a distorted cube. There's a cube at the center, and then there's sort of 6 distorted cubes around it. And so this is subdivided into 7 distorted 3 cubes. And so what that's telling me is that the 4 cube has 8 3-cube faces, and I can see how they all intersect by looking at this 3-dimensional subdivision. And so hopefully people are following what I've done. These are called Schlegel diagrams. Schlegel diagrams, which is a very nice way of visualizing a 4-dimensional polytope. And then one of the unusual 4-dimensional polytopes that was in that list that is very nice, you should take a look at it if you've never played with this before, is that there is a polytope in 4-dimensional space whose boundary consists of 120 dodecahedra. And it's hard to visualize that directly, but if you use the Schlegel diagram, if you have this polytope in 4-dimensional space that has 120 dodecahedra on its side, if you put your eye very close to one of the 120 dodecahedra, you can see the rest of the interior. You can see 119 dodecahedra in that 3-dimensional face, and this is the subdivision that you get. It's a very pretty object, and it's one of the unusual special regular polytopes in 4 dimensions. All right, let me switch back to what Jacques Tits was doing with Bourbaki. So in the 1960s, when Jacques Tits was introducing general Coxeter groups, he was writing down, how do you get from the diagram that encodes the dihedral angles back to these nice spherical or Euclidean representations of the Coxeter groups? And basically, if you had the set of generators and you knew the length of the Artin relations that pairs of generators, if you have Mij is the length of the Artin relation connecting Si and Sj, you can write these down in a matrix. And the matrix, the entry that you write down is actually cosine pi of minus pi over Mij. And you use this to define a symmetric bilinear form. And then once you have that symmetric bilinear form, you can actually write down geometrically, using this form, nice orthogonal transformations that are reflections corresponding to each of the generators. And the equation is just right here. This ends up being something that preserves the form, and it satisfies the relations that you want. And so in addition, what the major theorem that Jacques Tits proved is that, in fact, no matter what you write down as a diagram, no matter what integers you put on the edge labels, no matter what length Artin relations you pick, the Coxeter group W, where you've added the squares, the Coxeter group W always has a faithful linear representation into the orthogonal group of Rn, preserving this quadratic form. The important thing here is that it's faithful. And so once you know that it's faithful, then you always have a nice geometric representation of any group defined in this way. And you can use that geometric representation to study the group. In particular, you immediately have the solution to the word problem. If somebody gives you a product of a word in the generating set and their inverses, and they ask you whether this is equal to the identity, you just turn them into matrices, multiply them together, and see whether you get the identity matrix. That's a perfectly good algorithm. Let's do an example. So if you have the group that I have listed here, generated by ABC, with AB equals BA, BCB equals CBC, and then all of the generators squared to 1, then the matrix corresponding to this, it's going to have ones on the diagonal. A and B commute, so cosine of pi minus pi over 2 is going to be cosine of pi over 2 is going to be 0. BCB equals CBC, so this means Mij, the M in this case is 3. Cosine of pi minus pi over 3 is cosine of 2 pi over 3 is going to be -1/2. I guess that's this one down here. And then in the case where we look at A and C, I didn't write down a relation there. That corresponds to thinking of the Artin relation, there being no Artin relation. By convention, we say that that has infinite length. And so cosine of pi minus pi over infinity is just going to be cosine of pi is going to be a -1. And so we get this matrix that we use to define a quadratic form. And if you calculate this, the eigenvalues of this real symmetric matrix, you can end up seeing that it has 2 positive eigenvalues and 1 negative eigenvalue, which means that this is going to act on R3, preserving the surfaces of this form, or in other words, it's the usual sort of picture of the hyperboloid model for hyperbolic space in red, or the double cone in yellow, or the hyperboloid of one sheet in blue. And when you use the quadratic form from the previous page, basically you end up having 3 different types of vectors. The red vectors are the ones of norm -1, the yellow vectors are the ones of norm 0, and the blue vectors are the ones of norm 1 on the sheets that I drew. And of course, if you go further up in the red direction, then this was norm 1, but this will be norm 2 and norm 3, et cetera, or -1, -2, -3. And so the Coxeter group on the previous slide, this Coxeter group will act on something that looks like this. It will actually act as hyperbolic reflections on this hyperboloid model of hyperbolic space. In particular, let me go ahead and go to the next picture. You can think of it as being the Coxeter group with this diagram. A and B commute, B and C have relation order 3, A and C have order 0. And you can think about writing down a triangle with angles, with A, B, and C being the facets of the simplex, and then the dihedral angles being pi over 2, pi over 3, and 0. And that can be realized inside the hyperbolic plane, and you end up tiling the hyperbolic plane. Of course, the tiling would keep going. I only drew part of it. And like I said, this works for absolutely every Coxeter group. And so based on the nice examples of symmetries of regular polytopes and the groups that were showing up at the heart of the classification of Lie groups and Lie algebras, the semi-simple ones, Jacques Tits came up with an entire family of groups that were completely flexible, that all had faithful linear representations on a nice space. It might be a sphere, Euclidean space, hyperbolic space, but more generally, it will act on something with some more complicated signature, but it's always going to act on some nice thing. And if you take a nice simplicial cone coming from your fundamental domain and you start reflecting around, it ends up sweeping out something that's called the Tits cone, which is the union of the original simplices, simplicial cone. And the Coxeter group is going to act on that. In this case, it's ending up it's going to end up sweeping out everything that's in red. The Tits cone is going to be everything that's in red. which we can then think of on the slice of just the model of hyperbolic space. Okay, that was a brief introduction to the general idea of Coxeter groups. Let me skip that because it's a bit more technical. And so in general, we have all of these beautiful, wonderful properties for general Coxeter groups. Every Coxeter group is defined by a simple presentation. It has a faithful linear representation. As a geometric group theorist, there's a couple of nice properties that you might want. It's what's called automatic, meaning that you can calculate computation using a very nice finite state automaton. It's also what's called a cat-zero group. You can put metrics on these objects. You can actually build a piecewise Euclidean cell complex on which this group acts, which is non-positively curved in a very precise sense. Technically, this is known as the Davis complex with the Mousson metric. I'm not going to talk about that in this talk. But essentially, every Coxeter group just fits beautifully into many, many, many of the powerful theories of geometric group theory, and it's algorithmically extremely nice. Okay, so Coxeter groups, very natural, motivated by things that show up all over mathematics and has all of these beautiful properties. Now, in the second half of the talk, I want to talk about Artin groups, which are a little bit less familiar. They're, in my opinion, as natural as Coxeter groups. In fact, every Artin group can be derived from a Coxeter group. But I now want to talk to you about how mysterious they are. So let me first talk about what they are and how they arise. So how do you get from an Coxeter group to an Artin group? Let me make a very general definition here. So given any group acting on any space, let's assume that it's a reasonably nice group in a reasonably nice space, then you can always define something that you would call the braid group of the group acting on the space by saying the following. You say, let's remove any point that has a stabilizer, a non-trivial stabilizer. And then once you've removed the points with non-trivial stabilizers, the group is now acting freely on what's left. At this point, you can quotient by the free action of the group, and hopefully you get something that looks like a covering space map. And then after you've taken that covering space map, you can take the fundamental group of the quotient and call that the braid group of the group acting on the space. So this sounds like a somewhat complicated definition. The primary example, the classic example that really says this might be an interesting thing to do comes from one of the simplest actions of a group on a space. So probably the simplest action of a natural group acting on a natural space would be the symmetric group acting on n-dimensional real Rn, n-dimensional real vector space, just by permuting coordinates. And maybe let me go ahead and add in a page. Let's see. No, maybe not. That might be too complicated. If you have the symmetric group on 3 elements acting on R3, this is one where we can actually visualize it, then which points have stabilizers? Points are stable if they have 2 coordinates that are equal. And so you would end up taking R3 and you remove the hyperplane where the x coordinate and y coordinate are equal. You remove the hyperplane where the x coordinate and the z coordinate are equal. You remove the hyperplane where the y coordinate and the z coordinate are equal. So you're removing 3 hyperplanes. But when you remove one hyperplane from R3, then you end up breaking it up into 2 pieces. When you remove the second and the third, you end up breaking this up into 6 different pieces, each of which is contractible. And so there's not a whole lot that's interesting. The symmetric group is then going to permute the 6 different contractible pieces. When you quotient by the symmetric group action, you get the 1 contractible piece. And when you take the fundamental group, you get the trivial group. And so we didn't get something that was terribly interesting. But if we do the same idea on the symmetric group acting on complex space, where it's just, again, permuting coordinates. And again, let's think specifically about the case, the symmetric group on three things acting on C3. Then when we remove the hyperplanes, we're going to remove three copies of C2, the plane where Z1 equals Z2, the plane where Z1 equals Z3, and then the complex plane where Z2 equals Z3. But now, since we're talking about complex vector spaces, C3 has 6 real dimensions. C2 has 4 real dimensions. And so we're taking 6-dimensional space, we're removing 3 4-dimensional spaces. But when you remove a 4-dimensional space from a 6-dimensional space, it stays path connected. Because if you ever start coming towards the 4-dimensional space, you have enough room to go around the 4-dimensional space. It's not that easy to visualize initially until you know that there's a trick. And the trick is basically the following, that if you have a point in Cn, if you have a point in Cn listed by coordinates, then rather than trying to visualize Cn, which is 2n real dimensions, instead, what you can do is you can represent this point in this high-dimensional space by a sequence of labeled points down here in a single copy of C, just saying this is the first coordinate, that's the second coordinate, this is the third coordinate, that's the nth coordinate. And in this nice 2-dimensional representation, this nice trick, you can tell whether you live on a hyperplane. The first and the third coordinate are the same if Z1 and Z3 are plotted in the same point. And so to say that you're in Cn minus the hyperplanes is exactly the same as saying that when you take this vector and this single vector and you write it as a set of points, that you get n distinct points. If you want to try and think about what the fundamental group of this space is, you'd say, take this point here and start moving it around in some loop. As you move it around in some loop, the coordinates will change continuously. The points will move around inside the space. Avoiding the hyperplanes mean that they won't collide. And if you now take that path inside Cn and you trace it out over time, you start seeing things that look like braids. In particular, if it's a loop, it will come back to its original starting position, and the fundamental group of Cn minus this collection of hyperplanes will actually be what's called the pure braid group, because if it's going back to its original position, then in fact, every dot actually has to return to exactly the same spot so that you get back to the same coordinate. But if you then quotient by the symmetric group action first, before taking the fundamental group, then you actually get the ordinary braid group of how things braid together as strands. This particular example, so let's just think about what we did. We're taking the symmetric group acting on Cn just by permuting coordinates, and out of that, producing a space whose fundamental group is the braid group. All that really mattered was that we had a group acting on the space. We could have thought of this as the symmetric group acting on R3 by reflections. And then once we have the symmetric group acting on R3 generated by reflections, we can complexify it, remove the fixed points, quotient by the free action, and then take the fundamental group. And that would produce the braid group. And then this is how you generate all Artin groups. If you have a Coxeter group, a group generated by reflection or generated by involutions, generated by elements of order 2, satisfying very simple relations, Jacques Titz says that there's a way of turning that presentation of a group into a very beautiful geometric action on an object, where the generators actually become geometric reflections, and you can see everything about the group in the geometry of the group generated by reflections on this nice Titz cone. To create the Artin group, you follow the procedure that we just did for the symmetric group permuting coordinates. You complexify the Titz cone just by taking the exact same equations that you've written down in the past and just allow the solutions to be solutions over the complex numbers rather than over the reals. Once you've complexified the Titz cone, then you can remove the fixed points of the reflections, fixed points of all the points with stabilizers. At that point, the Coxeter group will be acting freely. And then once the Coxeter group acts freely, you can quotient. That's going to end up being a covering space map. And then you can take the fundamental group of this complexified hyperplane quotient, complexified hyperplane complement, the quotient of the complexified hyperplane complement, and say, what is that fundamental group? That's sort of a braided version of a Coxeter group. And Luinga's student, Harm van der Lek, in 1983, went through and computed the fundamental groups of these things for an arbitrary Coxeter group. And what he found was that these objects, these very, in some sense, natural geometric objects that are sort of complexified, braided versions of Coxeter groups, have extremely simple presentations, and that's where the Artin group presentations come from. So the simple presentations that we wrote down at the beginning, just nothing but braided relations, ABA equals BAB, ABAB equals BAB, ABAB. Groups defined by simple presentations like that all arise as fundamental groups of these quotients of complexified hyperplane complements that are coming from Coxeter groups acting on vector spaces preserving a quadratic form. And in particular, starting from the very simplest example, you end up getting the braid group out of this construction. Okay, so that's my story about where Artin groups are coming from. I should also mention that part of the reason people were looking at this is that people, in particular, the Arnold school was trying to classify in algebraic geometry all the possible structures of isolated singularities. And in doing that, they ended up focusing on the complexified hyperplane complements coming from the finite Coxeter groups. And this is where people really started working on these things. Let me mention, yeah, here's the remark. They first arose as the study of isolated singularities from the Arnold school in the 1970s. And to date, there are some Artin groups that we do understand. The ones that come from the spherical Coxeter groups, the braided versions of the spherical Coxeter groups were understood. And I'll say what I mean by understood in a second. In a couple of papers in 1972, one by Pierre Deline and one by Brieskorn and Saito, they had two very different types of arguments, but they both essentially showed how to understand the groups in the case of the braided versions of the finite Coxeter groups. They showed that the complexified hyperplane complement space is a classifying space. It has a contractible universal cover, and that you can understand the word problem. You'll notice there's quite a bit of a gap before the Euclidean or affine Artin groups were understood. This is work of myself and a student, Rob Solway, in 2017, and then the showing that it's a classifying space was done by Paolini and Salvetti in 2021. So getting much more close to the present. There are low-dimensional examples that where we're talking about 2- and 3-dimensional objects that were understood by various authors back in the 80s and 90s. And there's been a few isolated examples, but other than spherical, Euclidean, and low-dimensional, the only examples that are not of those types are ones that are, again, very, very recent by Thomas Hattel and Jingying Huang from 2023. And let me sort of wrap up here by sort of really highlighting how different these two classes of groups are. So just going back, recall that just a few slides ago, I said every Coxeter group is defined by a simple presentation as a faithful linear representation, and it has nice computational properties, meaning automatic, and it has nice geometric properties, meaning that it's cat 0. Artin groups, basically, they're also defined by simple presentations. They're closely related to Coxeter groups. They've also been studied since the 1970s. Every Artin group that we can understand, meaning every Artin group where we can do something algorithmically, where we know what it looks like geometrically, and every part of an Artin group that we can understand, all the things that we do understand have very, very good algorithmic properties. They have very, very good geometric properties. And so it's natural to conjecture that all Artin groups should be well behaved. And in fact, I got interested in this topic back in the 1990s when I heard Ruth Charney give a survey talk on this about what was known and not known about Artin groups. And I was absolutely amazed at how much is not known about these groups. In particular, so much that's known about Coxeter groups is completely mysterious for Artin groups. And in some sense, this kind of talk is a lack of progress report, that even though it's been 30 years since I heard Ruth first speak about this, the progress has been limited. And let me sort of highlight how limited. So here are some of the things that people want to know. The group presentations look like they shouldn't have, they should be defining groups that don't have any torsion. But are they torsion free? We don't know in general. Except for the non-spherical ones, they shouldn't have a center. They should have a trivial center. They should have a solvable word problem, and the space that I talked about, the quotient of the complexified hyperplane complement coming from the reflection action of the Coxeter group on the Tits code, should be a classifying space. It should have a contractible universal cover. These are things that everybody expects. But the troubling thing is that even for this small graph that I gave at the beginning, we don't know how to solve the word problem. This is amazing to me. 4 generators, 6 relations. We don't know which word, we don't know if this has torsion. Okay, let me, this is a particularly simple kind of graph because all of the implicit labels are either 2s or 3s. The A and D not being connected is a label of 2. A and B being connected by an edge is a label 3. These are called simply laced in the language of lead theory. So let's talk about simply laced. If you give me a graph and then you turn it into an Artin group by just saying that if 2 vertices are connected by an edge, they commute. If 2 vertices are not connected by an edge, they commute. If they're connected by an edge, then ABA equals BAB. These groups, it's a large class, 1 for every simple graph. Basically, we know how to solve the word problem. If it's a complete graph, that ends up meaning that it's going to be low dimensional, so no commutation relations. If it's one of the nice Dinkin diagrams, type A, type D, type E, 6, 7, and 8, or if it's an extended Dinkin diagram, and that's it. Any other graph that you write down is one that we don't really understand. It defines a group we don't really understand. And so let's try and make this really, really explicit. So suppose you write down a bipartite graph. So you've got M vertices on one side, N vertices on the other, and everything on the left and everything on the right are connected by edges. And so that would end up giving us this kind of group. We've got a collection of generators A, collection of generators B. I've got a typo there. This should be N. And then the kinds of relations, all the A's commute with each other, all the B's commute with each other because there's no edges connecting them. And then every A vertex and every B vertex satisfy a braid relation. Okay. Looks like a very simple presentation, but if you try to work with it, basically we only know how to solve it in 4 cases. We only know how to work with it in 4 cases. The 4 cases being the cases where M times N is at most 4. And so Everything else, other than these that end up being corresponding to a spherical Coxeter group or corresponding to a Euclidean Coxeter group, everything else is completely mysterious. And even some of these are things that we haven't understood until very recently. Here's an even starker list. Imagine that you just have a graph that's a star. You just have one vertex in the center that's connected up to a collection of other vertices, and that's it. So this is saying that all of the vertices on the leaves are going to commute with each other, and you have one vertex at the center that has a braid relation with each of the others. This one is the three-string braid group. It was understood by Dane back in the 1910s. This one is the four-string braid group. It was understood by Artin in the 40s. This one is more complicated. This is the type D4. It corresponds to a finite Coxeter group, but not one that's coming from a regular polytope. This one was finally understood by Brieskorn and Saito and Deline in the 70s. This one comes out of my work with Robert Solway in the 2010s. And this one we still don't understand. It's about 30 or 40 years just to add one more edge to this. And this is what I mean when I say that Artin Groups are mysterious. They do have lots of connections to other parts of mathematics, but at the moment, we're mostly just looking out over this vast field of groups, and there's not that much that we can see. We think that everything's going to be nice and beautiful and well understood eventually, but we're still waiting for the perspective that gives us a big breakthrough that makes it all understandable. Thank you for your attention, and I'll stop there and take some questions.
Thank you so much, John. Very, very nice talk. Very beautiful. Yeah, I'm amazed from this picture of going from Coxeter group to this fundamental groups. Very, very nice and beautiful. Thank you so much. So, any question, please, if there is a question.
There's one in the chat, it looks like.
Yeah.
Okay. If we could find a faithful linear representation for an Artin group, then how much would we know about this group? The answer is quite a bit. But the other answer is that it's very difficult. If you think about the very basic group that's sort of the foundation for the entire series of groups, the braid groups, finding a faithful linear representation for the braid groups was something that was an open problem for 70 years. And it was only solved in 2000 by Stephen Bigelow and by Don Kramer. That faithful linear representation was then generalized to all the Artin groups based on finite Coxeter groups, which is great. But even for the affine Artin groups, we don't have faithful linear representations to this day. And so if we did find a faithful linear representation, we would have lots of nice information, but those are extremely difficult to find. And in fact, it took a lot of work just to do it for the braid groups. So in some sense, yeah, most of the questions I often get when I talk about Artin groups to people who don't study Artin groups, I often get questions like, well, can you put a nice metric on these spaces? And the answer is, well, if you could put a nice metric, then we could answer the word problem and we could do all kinds of things. But we can't. We can't. Can you calculate this? No, we can't calculate anything. We don't know anything basically about these groups, other than special portions of the groups and special groups. So for some groups we know a lot. For some portions of the group we know a lot. I should mention that this talk is sort of a short general audience version of a more specialist talk that I gave as a series back in 2017. It has the same title. It's called The Mysterious Geometry of Artin Groups. This was a 3-hour lecture series that I gave. There's more references there. There's more detail. There's some of the same pictures. But this sort of will point you to the literature about saying exactly how little we know. I guess I would also say that I'm actually, one of the things that's kept me working on this field is it always has felt like there's going to be a breakthrough right around the corner where we're going to finally understand the groups all at once. And I still feel that. And I think that it still is coming. And there's at least a sense in the field that we're sort of seeing cracks in the ice, that we're starting to see little pieces here and there where we're able to understand things that we weren't for decades. And so it feels like we're on the verge of finally understanding these groups.
Thanks. Any more questions? Okay, can I ask you a question, John?
Sure.
I mean, this kind of teach systems corresponding to Coxeter Group, if there is something like that for Artin Groups or?
No. Yeah, there's been various attempts to try and find something that would count as a root system for an Artin group. And there are some very interesting recent attempts. And I should maybe mention this. One of the things that's causing interest in Artin groups right now is that the algebraic geometers who are doing work connecting with mathematical physics have spent many years recently looking at things called Calabi-Yau manifolds. And when you try to study Calabi-Yau manifolds, you start looking at the category of bounded derived, the bounded derived category of a Calabi-Yau manifold, which is an example of something that I've never played with that's called a triangulated category. And so there are things called triangulated categories that arise out of all of this big machinery of trying to understand things in algebraic geometry. And the people who study triangulated categories realized about 15 years ago that there are Artin groups that act on triangulated categories. And from the Artin group actions on triangulated categories, they can actually construct a triangulated category with an Artin group action for every single Artin group. And from that, they have something that they might think of as a root system for an Artin group. Mm-hmm. It's very mysterious to me because I don't understand the triangulated categories. But then there's also something called Bridgeland stability conditions, where you take your triangulated categories and you look at maps over from your simple objects over to the complex plane, and you build a complex manifold out of your triangulated category. And for the triangulated categories with the Artin group actions, the complex manifold coming from the Bridgeland stability conditions ends up being the complexified hyperplane complement that's used to define the Artin groups. And so suddenly, from this triangulated category algebraic geometric perspective, they're seeing Artin group actions arising, and they're actually constructing the spaces used to define the Artin groups. And so there's connections then that direction where the stuff that goes on with Calabi-Yau manifolds might actually give us tools to understand Artin groups. Mm-hmm. And there's some attempts from that perspective that give us some candidates for what might be a root system. But it's a pretty technical direction to try and pursue. Mm-hmm. So yeah, that's one of the different things that I was mentioning. Yeah, looks like there's another comment in the chat. Is the Hecke algebra of the Coxeter group helpful for understanding the Artin group? The answer is yes and no. It gets close. It's sort of like it's on the way towards understanding the Artin group. So Artin groups always map down onto their Coxeter groups, and the map from the if you thought about the Artin group algebra and the Coxeter group algebra, you can sort of see that the Hecke algebra is in between there, but in some sense, the Hecke algebra is very, very close to the Coxeter group. It may not feel that close to the people who study Hecke algebras. It may feel like you've gotten far away from the Coxeter group, but in fact, you're still fairly far from the Artin group. It's still quite a bit of a jump to get all the way up to the Artin group. They are related. It is sort of somehow fitting between the two. but it doesn't get you all the way.
Okay, any more question or comments? So I also have another question.
Sure.
So this Japanese school of Saito and people who are working on extended affine Lie algebras and root system.
Yeah.
So they assign some Artin groups to nullity to extended affine root systems. So is there, I mean, do we have the same, they have kind of a Coxeter generalized Coxeter presentation for these groups. Is there any also a picture like what you said going from this generalized Coxeter presentation by complexification to some braid groups or something like that?
Yes, yes. In fact, this is when Saito originally was studying the extended affine Artin groups. What he was doing, if you, it's sort of amazing because the people in geometric group theory that I talk to mostly don't know what Saito has been doing. They haven't been paying attention to that. But what Saito really was doing is that if you look at the origin story for Artin groups, they were looking at these complexified hyperplane complements for the isolated singularities. Arnold has a classification, Arnold and his school have a classification of other kinds of singularities. And so once you get past the isolated singularities, the next simplest type of singularity is a line singularity. And if you look at the geometry coming from understanding line singularities, you end up producing the class of extended Artin groups. And so Saito was pursuing the next level in Artin's singularity classification when he developed the notion of extended affine Artin groups. And so it comes with exactly this picture.
Okay.
Yeah, it comes with exactly this picture, but then the presentation is different. It's got these extra relations.
Right.
And so then, of course, it leads to the work that you've done on extended affine Lie algebras and everything. But yeah, it's exactly from this, but it headed off in a different direction. And so the people in my field generally didn't pay attention. But I'm actually somewhat hopeful that ideas from extended affine, the extended affine world are actually, when I said that I'm optimistic about us having breakthroughs soon, it's bringing ideas from the extended affine world back into the world of Artin groups.
Okay.
Yeah.
Okay, thank you so much. Any more question or comments? Okay, thanks again. Thank you so much. And thanks all the audience. Okay, thank you. Thank you very much.
All right.
Okay.
Thank you, everyone.
Okay. So John, maybe we can have some, I mean, by email, we make some time to talk a little bit more about this extended affine.
Oh, that would be great. Yeah.
Okay.
Yeah. Yeah, let's do that. Yeah. Because I'm excited to tell you the way I think that the ideas from the extended world and how they're going to play out in the, yeah, let's do that. I'd be excited. It's just been a busy time right now.
Okay, right.
Okay, yeah, let's be in touch by email.
Yeah, it was very, very nice talk, John. I really enjoyed, and I think other people also enjoyed this exciting talk. Okay, thank you so much. And
yeah, thanks for the invitation.
Okay.
All right.
Okay, bye-bye.